I am behind. So give me a second and I'll get to my book. But 3.5 is just, I'm having a really hard time with it.
Yeah, it's not these. And I'm going to tell you, well, I'll tell you this. Tomorrow, is the test day. I'm going to do a review day tomorrow. But would you be able, but you wouldn't be able to be in the regular class tomorrow though, right? Because the office won't be closed.
Right. Because we're just closed today for Veterans Day.
Okay, yeah. Find that book. I'll give you a minute. This section won't take as long either, so I will give you just a minute to kind of get in there. I'm getting the YouTube stuff set up too. Okay. Let me know when you've got that, Megan. Hey, Jenny. We haven't started yet. So do you have Megan's looking for, she's got her book out or she's getting it ready. But do you have questions about 3.5? Okay, that's fine. You need to watch the video. That's gonna be the hard one. Tomorrow we're going to review. We're gonna review it. Okay.
All right, I found it. So
Okay.
the quickest one I can come to, 31.
Say it again, Megan. I'm sorry.
31.
On 3.5?
Yeah.
Okay, so 3.5. So going back, looking at number 31, it's on page, it's markers.
I guess I'm just confused, like how, because the vertical asymptote is -3 and then there's a hole at +3.
Yeah.
I don't know. I guess it just kind of tricked up my brain. So I just wanted to ask about it.
Yeah, no, this is a great question because it's got both, right? So it's a good question because we've got both things going on. This is not on, is it? Oh, hold on. Give me 1 second. Okay. So for vertical asymptotes and holes, they come from the restrictions in the denominator. So we've got to find the domain. So I'm going to do that first anyway. So find the domain. We'd have to say, well, x squared minus 9 can't be 0, right? And we solve this and we wind up with x minus 3, x plus 3 really can't be 0. Set each one of those equal. And we find out that x can't be 3 and x can't be -3, right? Does that make sense, Megan?
Yes.
Okay, good. So now, I mean, if we do the interval notation, which I'm picky about, it would be -3 to -3 union, -3 to 3 union, 3 to infinity. Okay, so but what really matters about what the question's actually asking, which is about vertical asymptotes and holes, is that for these restrictions, what x can't be, it's either got to be a hole or it's got to be a vertical asymptote. So if we go back to the original now and simplify it, so I'm going to write this as x minus 3 on top. We know that this denominator factors into x minus 3, x plus 3, right? Now look, if it cancels, it's going to, that the 0 or the restriction from where it cancels, that becomes a hole. So look right here, at the x minus 3 cancels. Well, that's x equals 3 as the restriction, right? 3 minus 3, 0. So B, see here. So I know my hole's going to be at x equals 3 because that's the factor that canceled. You know, remember if x minus 3 was the factor, then x equals 3 was the restriction or the 0. You know, we really talked about it as a 0 in the previous section. And then whatever's left over, so this winds up being 1 over x plus 3. Well, the restriction left over is x equals -3, right? That's going to be the vertical asymptote because that's the restriction left over. So after you completely simplify, if you have a restriction left over, that's a vertical asymptote. Okay. Does that help?
Yeah.
Okay, good. Now I'll tell you with a hole though, a hole has a y coordinate as well. So once you simplify this completely, if you know you've got a hole that canceled out, you've got to plug this x back in. So if we plug that 3 back into the simplified function, you'd have 1 over 3 plus 3, right? The x is right there, the 3 plus 3. So you get 1 over 6. So you wind up with 3, 1, 6 as the whole. Yeah. Does that help?
Yes.
Yeah, it is. This is 3.5 is the hardest section, hands down, hardest section. Okay. Is that good, Megan?
Yes.
Okay. Let's get rock and roll with 4.1, and we will tomorrow morning. I'll have a review, or we'll do a review in class for this test, and it'll mainly focus on 3.5. I'll tell you. I mean, you need to know 3.6 and 4.1, but I feel like the most questions I have are from 3.5. There's just a lot going on. It could, in a few ways, it could be its own test. 3.5 was Monday, so okay. So let's go back to 4.1. Now we got the exponential function. Before we talk about the exponential function and, well, the cool stuff it does. Actually, this lecture is not going to be that long. I don't go into the depth the book does about exponentials. It's just a me thing. I don't think you need it moving forward. So I'm gonna introduce some neat applications with them, and it's actually one of my favorite lectures of the entire semester because it's a real world application that can help us throughout our careers. Actually, we'll see this here in a minute. Okay, so first off, let's define it. It's f of x equals b to the x. Now this is a basic exponential. This b is called our base, and it's going to be some number that's greater than 0, but it cannot be 1. Okay, so that base right there has to be greater than 0. It can be like a fraction or decimal, but it just can't be 1. Okay, it can be, it can be big numbers too, 2, 4, 5, 6, whatever. And of course, x is called the exponent. And what's different about all the functions before compared to this one is that our domain value is in the exponent, right? Our domain value is in the exponent. So the beginning of this section is going to really be a little bit of a review from the intermediate class on those exponentials, how to simplify exponentials, because we're going to need it when we get to the next test. The next test is going to be over 4.2, 3, and 4, or 4.4. Sorry, 4.2, 4.3, and 4.4. And we're going to really need to remember all those exponential rules. So let's talk about a few of them to begin with. Let's look at an example. Let's say we've got f of x equals 2 to the x power. And we just want to graph it. Remember, the most basic way to graph something is to plug in values. So plug in x values and get back y values. And I'm going to choose a few x values. Let's do -3, -2, -1, 0, 1, 2, and 3. Okay. So I'm going to take these x values, I'm going to plug them in, and you'll see this winds up being a nice little review of exponents. So let's do that here. I'm going to plug in, let's graph it up here. So I'm going to plug in f of -3. So f of -3 would be 2 to the -3 power, right? We're plugging it into that equation. Remember, if we raise an exponent to a negative, to simplify it, we have to put it into the denominator, 1 over 2 cubed, right? And it became positive. You guys remember that from last semester? Yeah, we've slept a little bit, but it's there. 2 cubed is what, 8? So we get 1/8. Boom. That's one coordinate. So I'm going to try to graph that. It's kind of hard. I'm going to try to graph it. 1, 2, 3, 1. 1A, that's about right there. Okay. So -3 and 1/8. So let's do -2 now. Well, -2 would be 2 to the -2, which is 1 over 2 to the +2, right? So a fourth. Should give myself more room here. So 1/4. Okay, so -2, we're at 1/4. Hasn't really changed much, right? -1. Oh, 1 more. No. 2 to the -1. Well, negative, that's going to be 1/2, right? So I'm gonna write it like that just so it fits in there. So at -1, we're at 1/2. Now, these get easier, right? 0, if I plug 0 into an exponent, remember anything raised to the 0, doesn't matter what the base is going to come back 1. If I plug 1 in, 2 to the 1 is just 2. If I plug 2 in, 2 squared, that's just 4. We can do that one. All right. And 2 cubed is 8, right? 2 times 2. There. So the graph looks something like this. And notice it shoots off exponentially, right? Now, a few things about the graph. Exponentials have an asymptote. They have a horizontal asymptote. They don't have a vertical, but they'll wind up having a horizontal asymptote somewhere. This one has a horizontal asymptote right here on the x-axis. So we've got this horizontal asymptote at y = 0, right? Which is fine. And I'm not going to go into the nuts and bolts of the graph. Your book does. If you're just really intrigued by the graph of exponentials, you're more than welcome to look at that section in the book. What I wanted to look at really was the algebra behind this, because we're going to see that moving forward. Remembering that, hey, if we raise something to a negative power, it's positive in the denominator, stuff like that. And the graph does shoot off. And notice, all we're doing, we're going to do whatever the base is telling us to do. It's doubling each time. 2/8 is a fourth, 2/4 is a quarter, or I'm sorry, 2/4 is a half, 2/2 is 1, 2 1s is 2, 2 2s is 4, 2 4s is 8, right? It's doubling each time, and that's why it shoots off pretty quickly. I mean, then if we kept going in order, we're going to go from 4 to 8, 8 to 16, 16 to 32, 32 to 64, right? We're going to shoot off real fast, exponentially fast. Okay, not a big deal. Making sure I'm on. Yeah, and your book on page 444 and 445, the book goes over characteristics of the exponential function, and it's really about the graph of the exponential function. And I'm not worried about that. I'm not going to test you on the graph of these exponentials or transforming the exponentials. I've taught business calc, cal 1, cal 2, cal 3, and I can tell you it doesn't help you if you want to move forward, and that's why I'm not really worried about it. But what I do like talking about next, actually before I get there, I've got to talk about the natural base. So the natural base is base E. Is E, it's in your calculator. I brought my calculator. I'm sure bring it. Guys, we're going to be using our calculator a lot, like probably for the rest of the semester. So if you remember, bring it. There is a calculator app on your phone. Hold on. Put it on my phone. It's not too bad. It's called Calc 84. Hold on, I've got it on mine. It's right next to my Jimmy John's app. But Calc 84, I know it's hard to see there. But it's not the word. I mean, it kind of mimics the 84. There's pros and cons to it, but some of the buttons are a little different, or some of the functions are a little different. But if you don't have the calculator on, you can always download that. And I know it's free in both of the app stores. Okay, but the natural base E, what's nice is it's in our calculator. What happened was this number kept occurring in nature. So whenever we started developing, seeing these patterns in nature and trying to create models, mathematical models based off, natural occurring events, this base kept happening. This number kept happening. And if you want to see what the number actually is, you can put e to the 1 in your calculator. This means, approximately. So e, you have to hit second and then the ln button, okay? And it'll bring it up. It's hard to see right there. And then if you hit 1, it'll tell you it's 2.718. We'll round there. 2.718. And not that you have to have this number memorized or anything like that. It is like pi. It's irrational. It'll go on forever and ever and ever. But it just occurs a lot in naturally occurring equations, like when we're trying to model something that occurs in nature. It's very interesting that it kept popping up over and over and over again. Your book does an example of this. It talks about the northern Rocky, the population of the gray wolf in the northern Rockies. This is on page 448 at the bottom of the page. And it gives you a function, f of x equals, now let's write what f of x actually equals. It equals the gray wolf population. Gray wolf population in the northern Rockies. X is years after 1978. And what researchers realized is there was this pattern that was occurring where, gray wolves, just like all animals, once they start cohabitating, they start growing exponentially, right? Unless there's some outside force. They start growing exponentially. And the equation that the researchers found was 1.26 e, and this is raised to the 0.247 x, okay? 0.247 x. That's kind of cool. So if you wanted to know, what the model was for a certain year, let's look at like 1989. So what is the population? Oh, let's do 1999. Population in 1999. The model. Anyway, remember, this is the model. It actually tells us the actual population. We'll see how close it is to the model. So if X is years after 1978, 1999 would be 21, right? So X equals 21 because that's 21 years after 1999. We're going to plug it in. F of 21 would be 1.26 e to the 2.47 times 21. So 1.26 e to the 0.247 times 21. So you get 200. Now look, we're not going to round up. We'll always round down because we can't have a half a wolf or 3/4 of a wolf. So we're just going to round it to the nearest whole wolf. Okay. So it says, or this model says, look, if we're predicting that there will be 225 gray wolves in the northern Rockies in 1999. Now, if you go to the page in the book, on page 448, it actually says that the actual population is 337. That's not that bad, okay? That's not crazy off. It's only about 100 off. But in the scheme of things, that's not too bad for estimating a population. Okay, let's do 2006 now. So what about 2006? Okay, let's think about this. If I wanted to do 2006, that's what, 28 years after? And yes, I used a calculator. So 28 years after 1978 would be 2006. So we want to know, well, what's the population then? So I'm going to pop in 28. 1.26 e to the 0.247 times 28. So 1.26 e to the 0.247 times 28. Oh, 1270. We're definitely shooting off, right? Oh, wait, got to round to the whole wolf because we can't have half a wolf or 1/4 of a wolf or 3/4 of a wolf. That's not how it works. Okay. Yeah, look at this. I mean, in 7 years, we've jumped up to 1,270 wolves. That's pretty good. Okay. Megan, is this making sense? This is more about popping stuff in calculators and things like
Yes.
that.
Yeah.
Sweet. Okay. Awesome. Well, let's do 7 more years later. And this should be an exponential equation. This should really shoot off. Look, it looks like we gained about 1,000 wolves. Do you see that? From what was this? 1999 to 2006, right? So 7-year gap, we gained 1,000 wolves. Let's see in 7 more years what it's predicting. So what about in 2000? Is that 13, right? So X would be 35. So F of 35, I'm running out of space, 1.26 e to the 0.247 times 35. I'm going to go in here. I'm going to change this 28 to a 35. Whoa, 7,158. I know you're saying, wait a minute, shouldn't you round that up? No, we can't round a whole wolf up. That's not how it works. Okay, so 7,001. So look, I mean, this is the beauty of exponentials, right? And it makes sense. I mean, even if we just think of the biology aspect of wolves, whenever a male wolf and a female wolf, I don't know what the names of male and female wolves are, but when they have a litter, it's not just one puppy, right? It's multiple puppies. And if they survive and then they wind up going to find their own little happy other, significant others, and they have puppies, it's going to exponentially grow, right? And that's what this model is showing. It's just showing, hey, if an average amount of puppies survives the litter and then they keep growing, this is how quick we can see it grow each year, okay? And it's going to shoot off. And eventually, of course, I mean, it's nature. It's going to overpopulate. It won't, the area won't be able to sustain it. So things will slow down. But the model is only going to predict a certain way. It's hard for a model to change like that, especially with exponential growth, okay? Great. Now we get to my favorite topic of the entire semester. And I'm gonna go about this like you've really kind of never heard of it before. And I don't want you to think I'm talking down to you. It's because there's some people in this class, there's some students that haven't heard a lot of this stuff. And so I think it's important for long-term financial health, actually, that we're going to talk about these kind of things. And I'm going to tell you up front, I'm not an expert. I'm not a financial expert. Okay. Not claiming to be a financial expert. I'm a math expert. I will claim to be that just in this kind of area. And I just want to show you the power of compound interest and how it relates to something you can do throughout your career. So we're going to talk about compound interest now. And I'm going to use some words. I'm going to try to define them as we go along. So compound interest. Now, there's 2 ways to calculate compound interest. There's continuous and non-continuous. We're going to start by talking about non-continuous. Okay, non-continuous. The equation, which I don't expect you to memorize, you'll have it for the test. It's on page 450. But what you have to know is what to plug in. And the equation looks like this. A equals P 1 plus R over N raised to the N times T. Okay? Now, this is for the case where you've got a sum of money, a principal. Oh, I think that's LE. That should be LE. My bad. Principal amount of money. So you've got some amount of money and you throw it into an account, and we know the rate and how long you're going to leave it in and how many times it's compounded a year. Okay, so the rate is the interest rate. And now look, you've got to write it as a decimal. So that means, like, for example, if we had like 4.2% interest, your rate is going to be 0.042. Okay. This formula is going to look amazing if you leave it as 4.20 because it would read it as 420%. Okay. So you have to write it as a decimal. N is the number of compounds a year. And then T is the number of years. Okay. And what will happen is A is going to be the amount in the account after compounding. Amount in the account after compounding. So I'm going to do just a basic example, that a real world one actually, that we can do is on like just a CD rate. I believe CDs are compounded monthly. We'll just assume they are for this example. Let me get some more paper. I'll bring this up a little bit so we can have the equation. Let's say we inherit $5,000 from our favorite aunt. We get $5,000 from our favorite aunt, and we're like, you know what? We need to save this money because we don't need the 5,000 right away. Maybe she gave us like 7,000, and we spent 2,000 on Slim Jims and Diet Dr Pepper or whatever. But now we've got this 5,000 left over, and we want to save it. And so we're the way banks want you to save it is a CD, because what they do, it's called a certificate of deposit. And what they do is they give you a really crappy interest rate that they can almost guarantee. And they're going to take your money and they're going to invest it wisely and make a lot more money off of it. Okay. That's kind of how CD rates go. But let's look at this and you'll see what I'm talking about with the crappy interest rate. So I'm going to get on Google. Today is 11/11. Hey, Nigel Harris Day, if you are into Spinal Tap. And we're going to look up interest rates on CDs. Now we need a year. Let's leave it in for, let's see what CD rates are, because I think it'll pop up. All I'm doing is getting on the Google and I'm putting in interest rates. Okay, here we go. I'm going to try to find the best one I can find. 10 best rates, CD rates for November 2020. Okay, we got a 3. We'll do 3 years. Okay, so T is going to be 3 years. And right now, it looks like the best interest rate I can find, if you're Googling along there, Megan, if you find a better one, let me know, is 0.85%. Oh, that's so crappy. That doesn't even beat inflation, right? But that's the point. That this is what they can guarantee. Look, you are guaranteed this. So the trade-off is you are guaranteed 0.85% interest. But also the trade-off is, I mean, it's just bad. It's just a little bit better than putting it in your mattress, right? I mean, just a little bit. Okay, so we've got a principal of 5,000. We got a rate years. Now we're going to compound this monthly. Compound monthly. So what that means, if we compound monthly, N is the number of compounds a year. So, monthly means 12, right? And I think we've got everything. Okay, now look, guys, this is 0.85%. So that means we have to write it as 0.0085 in our equation. So I'm going to write this like I would in my calculator now, okay? I'm going to write this like I would in my calculator underneath here. So I'm going to say, if I want to find the amount after compounding, it's going to be 5,000 parentheses 1 plus, now my rate is 0.0085 divided by 12. And then I'm going to raise it and make sure to put in parentheses. Now, some calculators automatically throw in the exponent, which is fine. But I'm going to raise it and I'm going to make sure to multiply the n times the t, the 12 times the 3. Make sure that this is in the exponent. That's a common mistake when you throw this in the calculator. So, let's see here. 5,000 times 1 plus 0.0085 divided by 12 raised to, is it 3 times 12 or 12 times 3? Doesn't matter. See how like this one's automatically in the exponent? Kind of see that. Some of them, it makes you do that. It makes it look like this. It just depends on the calculator. Oh, I got a whopping $129. So 5,129. Of course, for this one, we're going to round it to the penny. So 0.09. So that is in our account after 3 years. So you made $129 in 3 years with it being in that account, which is, I mean, that's you haven't beat inflation. Inflation is typically 3%. So you've really, in a weird way, lost money for it being in that account. Okay. But that's not for me. That's for you, between you and your financial advisor. Okay. Okay. So let's say we're like, hey, this is a really bad rate. What if I put it in something that kind of gets a higher rate? Well, I'm going to totally make up an example here just for fun. And just to do another example of compound interest. Okay. Let's say we go to a bank, or let's say some financial advisor, and we're going to take our $5,000 again. Like, we're shopping around with this 5,000 because we think this is pretty bad. And another person says, you know what? If I invest this well, I can get you 8.5%. Okay, and you're like, okay, that's a lot better than 0.85%, right? I can get you 8.5%, and let's leave it in 3 years just to see what'll happen with 8.5 compared to 0.85. And for this one, now this is where I get to just make this up. We're going to compound it quarterly. Because if someone's investing it, they're not compounding it. They're just putting it in the stock market and see what happens. So compound quarterly. So that means we're going to compound 4 times a year. And we want to see what happens now with this amount. So I'm going to do A equals 5,000 times. Now remember, 8.5, that's going to be 0.085. Okay. 0.085. So we get 1 plus 0.085 divided by 12 raised to the, oh, wait, that's not 12 though, is it? For this example, it's 4. Ooh, let's put 4 there. 4 times 3. Because n is 4, not 12. That was the last example. Okay. Let's throw this in the calculator. Actually, I'm going to be lazy. Bring it back up in the calculator. See here, we get 0.085 delete. So divided by 4. And then we get 4 times 3, right? So it looks like that. 5,000 times 1 plus 0.085 divided by 4 raised to the 4 times 3. Boom. Oh, heck yeah. $6,435.09. Don't forget the 9 cents. $6,435.09. Yeah, this would be the smart move. Now, I'll tell you, no one's going to guarantee 8.5%. That's just not how it works. Okay. But if you look at the way the market works over three, really probably over 5 years on average, or 10 years, you can get about 8.5% if you invested healthy or invested in healthy growth funds. That's between you and your financial advisor. Okay. Questions, comments, concerns. Okay, I'm going to introduce the other formula, and then I'm going to talk about what I think is important for the rest of our careers. The other form, so this was the non-continuous. Continuous is found a little easier, and it's also found from that that natural base E. So for continuous, so for continuous compounding, it's going to be A equals P, that's that base E, raised to the R times T. Kind of like per plus. But the shampoo's still around, I'm not sure. And the P, R, and T are the same. P is our principal. R is our rate. And then T is our time, or we'll do years. Now listen, we don't need the other two. We don't need the N because we're not compounding it so many times a year. Remember, N was the number of compounds a year. We don't need that because this is continuously compounding. I'll tell you, this doesn't typically happen in like the real world of compound interest. This happens when we're modeling things in the real world. So let's just look at an example, just to try one. Let's say we go to some new age bank. They've got new age cool stuff, whatever, and they say, we don't do a compound per year. We do continuous compound because that's what all the cool kids are doing, and they compound continuously at let's say 6.25% for 5 years. And you're like, you know what? Let's not do this $5,000. We've done that one already. Let's say like 2,000. We got this $2,000, and you want to see how much you've got after it's compounding continuously at 6.25% for 5 years. So A equals, so we got 2,000. E, and we're going to raise it now 6.25%. That's 0.0625, right? You still have to write it as the decimal times 5. Okay. Take the calculator out again. I'm going to do 2,000 E raised to the 0.0625 times 5. 2,733 and 68 cents. We're going to round this one up. 68 cents, even though I doubt the bank rounds it up. Okay. Kind of cool. Okay. Kind of cool. So we turned $2,000 into 2,733. We know this is good because it's above 3%, inflation. So we're beating inflation each year, which is what matters. Okay. Questions before I go on to my favorite type of example. And this is my rant. I don't feel like I've ranted as much because we're in the Zoom class. If you had me in regular class, we would rant a lot more. I'd be more ranty, definitely. The Zoom class has stopped the rantiness. We're going to talk about 401k for a minute and why it's important. So 401ks are a pension account, or not pension, I'm sorry. 401ks are a retirement savings account that your employer typically offers. Usually employers at this day and age don't offer a pension, right? That's something that our grandparents and our maybe even our parents could have. Now, there are some fields that still offer pensions, like teaching is one that has a pension. And if you can think of other ones, let me know. But there's not a lot of jobs now and careers that do pensions. They leave it up to you to invest in yourself for retirement. And one way to do this is a 401k. So 401k is really all it is just a savings plan. Okay. There's some rules with it. It's not a big deal, but there are some rules. But typically what your employer will do will meet or match your savings into one of these accounts. Megan, I'm going to ask you, do you have one with your employer now? Like, do they match it just to get a?
I really don't know if they match it. That's awful, but I don't.
No, that's fine. That's fine. And but just to kind of get with where we're at, I know a lot of times it's 3%. I'll hear a lot of students say when I ask this question, they'll say, "Oh, if I put in 3%, they'll give me 3%." And that's kind of how it works. So we'll do one we'll make one up like that, Megan. Let's say we work at a place where it matches 3%. So what that means is, let's say you make, I'm going to do some math here. Let's say you make $40,000 a year, and 3% of that is $1,200. Well, you put in $1,200. Now this is over each paycheck, right? So let's say if you got paid 12 times, once a month, you're putting in $100, right? So you put in $100 a month, and your employer matches that $100. Okay, so that's how 401k typically works. Okay, and your HR person will explain that to you when you first get hired. but they'll match up to a certain amount. Some places are more. And some places it'll be like, you put in 5% and they'll put in 7%. Like they'll do goofy kind of matching that way, but that's fine. We're going to keep it easy though and go with this. We're going to say, let's say you get out of school, you get your degree, and you start off making $40,000 a year, and your employer says, "Hey, we have a 401k match program because we don't do retirement pensions, and if whatever you put in up to 3%, we will match." So this is free money. Okay. So let's look at this after 1 year. Now, look, this isn't an example. This isn't perfect, because what happens is what you do with this 401k money is you invest it in mutual funds. So it's following along with the stock market. So it's not a perfect, compounded daily, quarterly kind of thing. It's just moving along with the stock market. Okay. But we're going to give kind of a theoretical model of what typically happens. Okay. So let's say you put in 3%. So that's $1,200 the first year. And your employer is going to match that over the year. So we've got a principal here of $2,400. Okay, kind of cool. And half of it isn't even your money. It is your money, actually. It's free money. They build it into your salary. That's why you need to use it. If you don't use it, your employer gets to keep it. I don't like that idea. It's my money. My money. Okay, so your principal is $2,400. Now, this is the part where I get to totally make up stuff. But I'm going to do educated guesses while I'm making it up. Let's say if you invest this into mutual funds, let's say we can get 9.1%. Now we have to leave it in there a long time to get an average of 9.1%. Okay, so that's 0.091. Now remember, I'm making this up. Let's say you're fresh out of college. You're 20, we'll say 24. Okay. And this is your first year of working. You're going to put this in your first year of working. You're 24. This is a retirement account. You can't even draw it out unless you want to take a huge penalty. You can't draw it out till you retire. When do you want to retire, Janie? What age do you want to be? 60 sounds great. So 60 minus 24, that's 36 years. This is going to sit in an account 36 years and just simmer and cook. It's going to go through recessions. It's going to go through presidential changes. It's going to go through pandemics, right? And it's just going to sit there and keep cooking over 36 years. So now I've really got to make this next part up. We've already compounded quarterly. Let's just compound semi-annually. Semi-annually. That's something that pops up. Now, this is what's not really true because it's in an account, right? Or it's in a stock account. So it's going to do this stuff the whole time. But I'm going to make it up. We're modeling what can happen or what does happen. Actually, it's pretty close. Let's see what we have after 36 years. So $2,400 times 1 plus 0.091 divided by, semi-annual would be 2. Raised to the 2 times 36. Okay. $2,400 parentheses. It doesn't matter. I could have done times, I guess. But you need a parentheses. 1 plus 0.91. 0.091. Divided by 2. Raised to the 2 times 36. Dang. $59,093. What? Now, this isn't perfect. I cannot guarantee you this. That's not what I do. Okay. But the idea, and it's probably a little inflated. I'm going to be honest with you, because it probably comes down and it goes back up. I mean, you're going to have years that it goes down to like to 1 or 2% or no percent, right? There's been years in the past that have no percent, but there's also been years where we've gotten 20%. So that's why we're kind of evening it out. But it's all based on you letting it cook for 36 years. This is the exponential part of compound interest. Okay. And the stock market is exponential. If you look at the stock market, the way it rises is in an exponential manner. Okay. It does not rise in a linear fashion, right? It's not like it just rises, at 100 points a year or something. It's nothing like that. It rises exponentially. Okay. Now look, this is your first year of savings. Now the next year of savings won't be able to cook as long, but you'll be able to put some more money into it, right? Hopefully you'll get a raise. You get a new job. You'll start making more money. So you put a little more money in. But I'll tell you, you can beat it if you get a nice huge raise, but nothing beats that cooking that long. Okay. Nothing beats those years. Like, let's do another. Okay, come on. There have been a lot of advances in the medical field, right? And you get to 60. Janie gets to 60. She said she'd retire 60. Janie gets to 60 and she's like, man, the 60 is the new 30. I love what I'm doing. I'm going to work for another 5 more years. Okay. So the only thing I'm going to change here, let me kind of undo this over here now. The only thing I'm going to change is the number of years. I'm going to keep it at 99.1%, but instead of 36, I'm going to work for 5 more years. So 41. And you're like, I'm not going to touch my retirement. I can't even get Social Security until I'm probably 67. I don't know what Social Security. I have no idea. But it's not 60. So I might as well just keep working. So I'm going to do the same equation, but the only thing different is instead of 36, we're going to do 41 because we're going to work 5 more years. So 2,400 times 1 plus 0.091 divided by 2, raised to the 2 times 41. Now, if you hit second enter, you can bring it back up in your calculator and just change the 36 to a 41. Holy moly. 92. Look, these results are not typical, right? 92,210 and 91 cents. Okay. Now, look, I'm going to tell you, these are really inflated numbers, but they're in a range of numbers. What if you go to a market or a financial advisor, they're not going to give you like an exact amount. They should give you a margin of error. This would be in the margin of error for this. Okay. For $2,400, if you let it cook for 41 years, which is the hard part, right? Letting this sit there for 41 years is very hard and not touching it. Okay. So $2,400 for 41 years at a 9.1 interest rate, you're going to wind up with $92,000. That's crazy. That's great. Okay. It's a lot. I can't promise you this. I'm putting that caveat onto all of this. Okay. But that's how compound interest works. That's why you need to do this as soon as you can. Okay. And even if it's as little as you can, even if you make a lot less money, if they're matching it, you need to do it because automatically you get 100%, right, return on your money. And you put it $1,200 and they match $1,200, you're getting 100% return on your money before you even put it in the account. Okay. So think about that. I mean, that's really, you've made this off of $1,200 because that's the amount you've put in, which is even crazier. Okay. So that's my rant. That is you need to put money in your savings account, your 401k account as soon as possible, because that's really what's going to keep you from having to rely on other people when you retire and get that old and crusty. Okay. Do that as soon as possible. ASAP. Okay. For homework, there's not a lot of homework in this section I want you to do. 4.1, the very beginning stuff is just how to use a calculator, 1 through 9. And then 53, I want you to do all of these because there's not a lot. So I want you to do the evens as well. 53 through 56. And then 65. If it asks you to graph the question, do not worry about graphing the question. I want you to do the actual, like the numbers stuff, the part of the question. Let's do 65 through 74. And this stuff's the application, this stuff at the end. It starts on page 451. Page 451. Okay. Any questions, Megan? And we'll review tomorrow. So if you think of, Megan, if you're, I know you won't be here in the morning, but if you have a question that pops up in your homework when you're working this evening, just shoot it to me and I will cover it in the lecture tomorrow.
Okay.
Tell Riker I said hi.
I will.
Okay. Okay. I'll see you guys. Do you have any questions, Megan?
No. No,
Okay.
I'm good.
Okay. I'll see you. You have a good one.
All right, you too.